Allow me to introduce my colleague, Dr. Frank Stefani from Helmholtz-Zentrum in Dresden-Rossendorf. Frank finished university in 1988 at Technical University in Dresden. He finished theoretical physics and then continued his PhD at the University of Leipzig and finished 1995 also in the area of theoretical physics, and then changed to fluid dynamics. And since 2011, is a research fellow in Dresden-Rossendorf. Also earlier worked there as a research assistant. And now Frank works on hydromagnetic experiments. Was part of Riga Dynamo experiment in Latvia, and also many other projects and cooperations. Now Frank is a principal investigator of so-called DRESDYN Dynamo experiment, which is preparing now. And today we'll talk about the laboratory experiment on the generation and action of cosmic magnetic fields. So Frank,
yeah, thank you very much for this kind introduction. I'm very happy to be here. It's a great pleasure and also honor to come here to Prague, to this institute. And I have to say that during the last years, I have more and more appreciated the great work that has been done at this very place by people like Václav Bucha, Ivanka Shavatova, Pavel Haider, who is here. I'm very happy that he joined us. And I will come at several points to the work, back to the work that has been done here in Prague at this institute. And it has to do with the geodynamo, with the solar dynamo, with the solar climate interaction at several places. I will come back. This is the structure of my talk is approximately as follows. The main part will be devoted to the effect how cosmic magnetic fields are generated. So here we speak about the famous hydromagnetic dynamo effect, which is known to produce the magnetic field of the Earth, the Sun, galaxies, stars, of course. And a short part of my talk at the end will be, because here we are in geophysics and not in astrophysics, and the other institute it would have been a little bit larger. This is about how cosmic magnetic fields, once generated, how they can influence cosmic structure formation by several instabilities. Most notably among them is the magnetorotational instability, which is responsible for the accretion of matter into protostars or black holes. This is a very, very important instability. And this will be the second part of my talk today. To give you a very, very short introduction into the mechanisms I'm going to speak about. So here is a dynamo. So imagine you have a magnetic field within a conducting fluid. And now imagine that you have a sort of chiral helical flow structure, and it must be conducting, and you need a certain product of conductivity, length, and velocity. And under certain circumstances, this helical velocity can produce an electrical current, which is then capable of reproducing the magnetic field. And if this effect becomes strong enough, if your amplification becomes infinity, so to say, you get self-excitation of a magnetic field or dynamo effect. The instability, which I show you here, has another character. It is the here I show you the magnetorotational instability. There has been for many decades a problem to explain how central objects in the cosmos are formed. This applies to protostars, this applies to black holes, because they would like to eat up some material from the accretion disks around them, But the equation disks, they undergo a Keplerian rotation, and Keplerian rotations are extremely stable from the purely hydrodynamic point of view. So there is no good reason for the particles to fall into the black hole or the protostar, say. So what we need here is a mechanism which couples angular momentum from inner fast parcels to outer slow parts. And this can be accomplished if the accretion disk has some ionization, some conductivity, then magnetic fields, if they are there, act like rubber bands or like springs, and they do exactly this. They couple the fast elements inside to slow elements outside. So by this mechanism, they transport angular momentum because they accelerate the outer ones and decelerate the inner ones. And then the inner ones fall into the black hole and the other ones go more outside. And this is the so-called magnetorotational instability in a very, very rough manner. So I'll show you not very much formula today, but the most important are the Navier-Stokes equation for the velocity, which is written here. It's, you know, it's a nonlinear equation. Here is the time evolution of the velocity field u. Here is a nonlinear term. Here is the gradient of the pressure, which might also include, there might also be other forces, buoyancy, whatever, Coriolis forces. Here is a dissipation term with a viscosity here. And here's a term, if we have a certain magnetic field, then we get a Lorentz force which acts back or which acts on the velocity. So you have an effect of the magnetic field on the velocity. So the governing parameters for this equation are the famous Reynolds number. I think you all know what is a Reynolds number. It's a length times velocity over viscosity. And if you have a magnetic field, then its influence is governed by the so-called Hartmann number, which gives you a strength of the magnetic field weighted by the conductivity, so to say, and with some viscosity. This is the hydrodynamic part. Then comes the magnetic part. If you combine pre-Maxwell's equations in an appropriate manner, you end up with a unique equation only for the magnetic field. You can throw away the electric field. You get an equation only for the magnetic field, and this is called induction equation. And the structure is as follows. You have the time derivative of the magnetic field. Here you have a term which is a Laplace B, which always destroys magnetic field. This gives you ohmic dissipation, Joule heating, so to say. So this makes, yeah, it destroys magnetic field. And here's an interesting term, curl U cross B. This means, it's a complicated term, curl U cross B. But if you have a velocity inside, and if this is appropriately formed with some helical structure, you get a chance that this term becomes larger, that this production term becomes larger than this destruction term, and you might get a positive time derivative. You might get even exponential increase. And the ratio between this term and this term, you can go into the numbers a little bit, is the most important number of magnetohydrodynamics. It's called the magnetic Reynolds number. It has the same structure as the usual Reynolds number. Here, length times velocity, but the prefactor is, this is just magnetic permeability, but here is sigma, the conductivity. So everything what we are doing is, in a way, governed by the product of conductivity, length, and velocity. Please keep it in mind, three factors which are important. So coming back to the structure of my talk, this I have stolen from my student Martin Sallmeyer, who likes to speak about the yin and yang of cosmic magnetohydrodynamics. So what we have is, we have velocities. It might be u or v. It's not very important. These velocities, if they are strong enough, might produce, via the homogeneous dynamo effect, magnetic fields, B. And under circumstances, those magnetic fields might be capable of destabilizing flows V, which are supposed to be hydrodynamically stable. So this is a magnetorotational instability, Taylor instability. I will also speak a little bit about Alvin Waves at some point. So here we have the field production, here we have the destabilization of flows, and then there might be, and this is a very modern development, a sort of dynamos of a higher kind, or where both effects are supporting each other, where a magnetic field destabilizes a flow, makes a turbulence, and this turbulence produces the magnetic field, which is then capable of destabilizing the flow. So you get a higher order dynamo. And these types are called MRI dynamo or Taylor-Sproyd dynamo. There is since maybe 10 years or 15 years some activity here, but I will not speak very much about this. In my first part of the talk, it's a bigger one. I will speak about the dynamo, and here we need Rm, the magnetic Reynolds number, to be large to have this effect. Okay, let us come, we are here in the Geophysics Institute, let us come to some little history. So I think magnetic fields have puzzled people since a couple of thousand years. So when you look into Aristoteles, there is some mentioning of that Thales knew already about the attracting power of lodestone. So the Chinese and the Olmecs, they had very funny types of a compass, so wonderful. And what I always like most is this book or this work of Petrus Peregrinus from 1269. And Petrus Peregrinus made first nice experiments with lodestone. And what he did, you might look into his book, it's really fascinating. And what was the most fascinating is this one. Here, the polarity has been introduced into scientific culture in physics. He detected if he takes such a beam like lodestone, he breaks it, and then he puts it like this together, it's attracting. Naturale, he was Italian, naturale. And then he took this, put it here, non-naturale, repulsion. And he noticed it's not only what people like Thales also believed, it's always attraction, it's not. It's repulsion and attraction, and depending on the polarity, of course, you know. And here we have, this is naturale, naturale, and here's non-naturale, non-naturale. This is the introduction of the polarity into physics, 1269, amazing. 3 centuries later, William Gilbert made even more systematic experiments with spheres of lodestone. And this is a wonderful book. You can still buy it at Dover. And here's a nice experiment here. He took a sphere and applied some little mountains here, some little volcanoes, if you like, and put it here. And then he took compass needles and look at this. This is looking a little bit more to this volcano here, and this is looking here. And this was what he knew already from the Earth's magnetic field. And he concluded conclusively, the Earth is nothing than a big lodestone. Very well substantiated, I would say. In reality, it's a little bit more complicated. And it happened that some 40 years later, it was noticed by some people that the declination of the compass needle is changing in time. And this is, of course, not easily explainable by such a lodestone model. And then some people tried still to rescue this theory. And among them was Edmund Halley. Halley made a paper here in 1692. Okay, let's assume we have our Earth here, and it's made up of different shells of lodestone, and they are moving respectively to each other. And by this motion, you can change the declination of the needle. Very clever idea, simply not true. So what we know now from the seismics, of course, we know it from seismics. We know we have the crust, we have the mantle, we have the liquid core, and then we have the solid core, mainly of iron. Nobody knows it better than you. And the picture of the magnetic field generation of our Earth today is the following. So here is a mantle outside, don't show it. And here is the liquid iron, and here's the inner core. And the traditional way of thinking is that here, when the inner core solidifies some light elements, sulfur and so, they remain and they come under the influence of the buoyancy, it's going out. And then you have a fast rotation. So you have Coriolis forces. And both together, radial forcing and Coriolis, they make exactly what we need. They make a helical structure, or many of them. Many, many little helical structures filling the outer core of the Earth, and they are believed to produce the dynamo, the magnetic field of our Earth. The induction equation, which I showed you, is a little bit complicated. It looks like a Schrödinger equation in quantum mechanics, but it's a vector equation. And this curl U cross B makes it a little bit complicated. So it took really some time, much longer than in quantum mechanics, to solve some paradigmatic cases for the induction equation. But finally, it was done in the 50s, 60s, 70s. People tried to solve this equation, and the big breakthrough happened in 1995. I think, probably Jan, you know this very well. This was on the cover of Nature, and it was a paper by Gary Glatzmeier and Paul Roberts. And they simulated the combined Navier-Stokes equation plus induction equation for the core, radial forcing, buoyancy, Coriolis force. And what they got was reversals of the magnetic field. And this was a big hype at this time. So what you see here, imagine this is the outer core. Outside our magnetic field is more or less dominated by a dipole, a little bit quadrupole and octopole, whatever, but it's mainly dipole. But inside, it's much more fingered, it's much more interwoven. And you see here this structure which is produced by these little helices in the outer. And then, I don't know, a few thousand years later, they saw the dipole is gone. There is no dipole anymore. And still a few thousand years later, the dipole is again there, but it has reversed. So this was a big event in the numerics of the geodynamo. And of course, we know, so we have reversals approximately 3 per million years, more or less chaotically, but not exactly. I will come back to this in a minute. And yeah, this was believed to be one reasonable simulation of one of those reversal events. I should tell you that Jan is also working on this with his code. He's studying different parameters, magnetic Prandtl number, and so on. So many people are working on this. I would like to show you a more recent paper by Nathaniel Schäfer and Dominic Cho and so on. You see here already the fine scales which people are now trying to resolve. So grid spacing is a big issue. It's amazing what you see here. So look here, this is the concentration, the radial velocity, and magnetic field strength. So they really try to go very, very deep into the structures, which is fantastic and great. Still, it's far away from all parameters of the real Earth. So with the biggest computers, we have no chance to do anything like the Earth does because we have a turbulent flow. And one of the most important numbers is the so-called Ekman numbers. This is the inverse of the Reynolds number, if you like. This is for the Earth 10 up to minus 15. What you can achieve here roughly is 10 up to minus 7. So we are still 8 orders of magnitude off. Here's a magnetic Prandtl number, 0.1. This is in reality 10 up to minus 5. We are really far away from the real parameters of the Earth. And this is one of the epistemological reasons, so to say, why we not only want to do simulations, we would like to do experiments. First, we would like to check simulations. Are they correct in this turbulent regime? But there is also a more, I would say, philosophical point of view. And this was written here by the famous Richard Feynman shortly before he passed away on his blackboard. He was a great theoretician, and even he told us, what I cannot create, I do not understand. I think this is really deep. This is really deep. Always try to build something. And if you try it, you understand it better, not only simulating, but also building. And I would like to show this because it has really some, I think, some deep. Okay, so we would like to go from numerics to experiments. And we noticed quite quickly, this is costly. And the reason for this has to do with this terrible magnetic Reynolds number. Sigma, the conductivity times velocity times length scale. It must be, the first term must be larger than the second, definitely larger than 1. This is a minimum, better larger than 10 or 100 or 1,000. So this is, below this, has no chance to start such experiments. So this means in the first instance, we need liquid sodium, because liquid sodium is the best liquid conductor you can have. It's cheap, it's not very heavy, has a high conductivity, but it's dangerous. So all these experiments I'm speaking about today are quite dangerous, but there is no other chance. Then you might ask, okay, sigma times U times L. I can trade a little bit between U and L. Sigma fixed, I can trade between U and L. I can make the machine like this, make it faster. The point is only, if you have a turbulent flow, we know that the power, you know it from wind turbines, the power always goes like Reynolds to the Reynolds cube over length, or magnetic Reynolds number cube over length. And this means if we have to fix this guy here, Rn, so we need more power, the smaller the devices. So, and you always end up with some trade-off between size and power. And all the machines I will show you today are approximately something like 1 meter. So 10 centimeter would be possible, but then you would need 10 megawatt motor, not only 1 megawatt. And this is always such a trade-off, and I will show you all the machines are on approximately this size. Since more than 20 years, we have a really very funny community of a few groups in the world who are trying to do MHD experiments in those extreme parameter regimes. So on the dynamo side, I will show you more about the Riga experiment, the Karlsruhe experiment, the VKS experiment, and then about our DRESDYN experiment. There are other most interesting experiments. On the side of the MRI and magnetically triggered instabilities, there are also a couple of experiments. Here's one in Princeton and here in Socorro. And I will speak only about our experiment in Rossendorf because we have not so much time today. I come now to the Riga experiment. The Riga experiment was running for the first time in 1999, but it had been prepared by Agris Gailitis in Salas, close to Riga, since 25 years before that time. And the idea is extremely simple. We have said we need a helical flow. And he said, based on the work by Ponomarenko, no, let's take a helical flow. One, let's take a big helix. If you take liquid sodium, you cannot take an infinitely long helix. It's too costly. Infinity is always costly. So you have to drive it back. So what you get is here, this red one is a helical flow, 3 meters height, 25 centimeters diameter. And then this is turned back here into this propeller ridge. And then you see here 2 old Russian motors in Latvia with giving 200 kilowatt of power. And then you can drive, and we have optimized for quite a couple of years this structure here with a propeller with pre-propeller vanes, post-propeller vanes, in order to get a maximum of helicity for a given kinetic energy or power, so to say. We spent really years in order to optimize this, and it paid off. It paid off. Okay, what you have then is the structure here. This is a picture, and the magnetic field structure, which is coming out of this equation, is a so-called, like in quantum mechanics, it's an eigenfield of the induction operator, so to say. And it has a certain structure and a certain frequency and a certain growth rate. It has a complex eigenvalue. And the structure is like so. You see, it's a double helix. This one helix of the flow makes a double helix of the field. It's quite amazing, quite nice. I have a little problem with the videos here, so I cannot show you, but you can believe me, it's just rotating. So in 1999, we, after a lot of years of preparations, and we entered this business in 96. We did a lot of simulations and so on. We made first experiments with this complex machine. And our first ambition was, okay, let's start at high temperatures, low conductivities. Let's look not for self-excitation, but simply for amplification. So we had some wires wound around. We were looking for amplification. We got very nice amplification factor 20, great. So you apply. But amplification is not self-excitation, it's something different. And this was a very funny evening. And only the next morning we noticed that there was some 15 seconds where, in addition to the pre-given 1 Hertz signal, which was simply amplified, there had appeared another one, 1.3 Hertz. And in hindsight, we noticed this was self-excitation. So we had it for 15 seconds, but after this 15 seconds, we had to stop the experiment due to some sodium came out of some bearing, so we had to stop. And anyway, so we had a first Fisher Letters paper about this because we had seen for 15 seconds self-excitation. So this magic threshold had been crossed. Half a year later, we made very nice experiments, very clean experiments now, and here's one of the very first which gave us extremely clean results. What you see here, here's the time, here's a magnetic field. Blue is the rotation rate of the propeller, and you see we are cranking it up to some 2000 RPM. And the red one is a measured magnetic field. It's a little bit patchy simply because it's oscillating, but it's just oscillation plus exponential increase. And this you see here. You start from a sort of nothing, and then you see here that it's increasing over many orders of magnitude. It's a perfect exponential increase of the magnetic field. It's a fantastic self-excitation which we observed here. We did plenty of experiments here, and if you are interested in all this, we have summarized all the experiments, all the results in a recent paper, Journal of Plasma Physics in 2018. You might have a look. There are many, many more results here. Here's another one from 2005. We crank up the rotation rate, go down, crank up again, bum, 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 bum. And you see here, you can switch on and off your dynamo by will. It's really going up and down. We have also tried to understand the back reaction. The back reaction sets in here. So we have exponential increase over many orders of magnitude, and then we get an equilibrium. What happens there? You know from school Lenz's rule, if you have induction, you get a current which in the magnetic field produces a force which acts against the source of its own generation. You can do it with a pendulum in a magnetic field very easily. Lenz's rule. And we have tried to understand Lenz's rule for this more complicated rigor machine, and it works perfectly. You can take this eigenfield here, compute the current, compute the Lorentz force, G cross B, and what you get then is, at least the axisymmetric part, a force structure. The radial is not very interesting, but here is the axial one. This is positive, this is negative. This acts against the downward flow, this acts against the upward flow. Here it's the azimuthal force. This acts against the rotation, this accelerates. So all the forces which are produced act in a perfect way in the sense of Lenz's rule, and they counteract the dynamo source. And then you get an equilibrium between the forcing and the appearing magnetic field. So we have done a lot of studies about this. One of the most important one is, apart from the structure, here is the growth rate over the rotation rate of the propeller. Here is the frequency over the rotation rate of the propeller. The red ones are in the so-called kinematic regime, where you expect no back reaction. The blue ones are in the saturated regime. So you see here, the blue ones for the growth rate are by definition zero, because you are in the equilibrium. And the frequencies are here. The points are always measured values. The lines are our simulations. And what you see here, it's more or less a quite reasonable agreement by some 5 or 10%. So we can really describe by our numerics this kind of dynamo in a quite good manner, I would say. And again, as I said, if you would like to see more results on this, please go to this paper, Galides et al. In the Journal of Plasma Physics. This was the first experiment in '99. And funnily enough, months later also, after decades of preparation for both experiments, which are huge, a second experiment became operative in Karlsruhe in Germany. And before I show you the machine, I would like to come to the theoretical basis here. The theoretical basis is the so-called alpha effect. What is alpha effect? Alpha effect was, at least in a cartoon-like manner, invented by the famous Eugene Parker. You might know the Parker solar probe. Parker died 2 months ago, in the 50s. But the mathematical foundation was laid by Max Steenbeck, Fritz Krause, Karl-Heinz Wedler in the 60s in Jena in East Germany. And they wrote a very funny paper, Berechnung der mittleren Lorentzfeldstärke für ein elektrisch leitendes Medium mit Turbulenz durch Coriolis Forces. It sounds very funny in German, so it's a little bit old-fashioned. But anyway, what they detected is the following. They described the alpha effect. And the alpha effect, I hope that the video is running. By the way, it was done by Andre. So what you see here, or not, no, sorry. Yeah, okay. What we get is the following. You have a magnetic field line, and if you have a helical flow, then you push the magnetic field line like this, and then you rotate it. And if you consider this rotated magnetic field as one loop, you can take right-hand rule, and you get a current which is pointing in this direction. So you get something very unusual. You get a current which is pointing in direction of a magnetic field, which is very counterintuitive given what we have learned in school, a current parallel to the magnetic field. And this is the alpha effect. Okay, and then Karlsruhe people, Robert Stieglitz and Ulrich Müller has built this machine, which is a realization of the alpha effect or alpha squared dynamo. And here, in contrast to the Riga experiment, where you have one single helix, they put 52 little helices together, which are simulating a sort of Earth's core with as many, many little helices. And it can be described nicely in terms of an alpha effect. And you see here again, it's a big machine, 1 meter. And you see here the structure. And indeed, in December 99, they observed with this machine a fantastic self-excitation. You see here the magnetic field going up, or also by, what is it, Gauss, 60 Gauss here, you see it here. It worked in a wonderful manner. It's also a very nice dynamo. Okay, the third dynamo, which became operative a little bit later, was the so-called VKS dynamo von Karman's sodium experiment in Cadarache in France. This machine is essentially a cylinder where you have two counter-rotating impellers making a funny motion, which is like this, but also with some poloidal flow. And this is supposed to be a good dynamo. And they were very optimistic to get a dynamo, but it did not work. For a couple of years, it did not work. Then many people try to understand this, and we also, and we noticed that the flow here behind these plates is quite critical for the dynamo. It destroys the dynamo. So they decided to make a trick. They said, okay, let us simply screen the induction effect from behind the impellers by using high magnetic permeability plates. This was the idea. They did it, and suddenly the dynamo worked. And this is really fantastic because by changing the two types of rotation here in their relative amplitude, they can get fantastic effects. They can get dynamo like this, steady, nothing special. But they can also get extreme spikes. And what they can get here, they can get reversals, as our Earth does. And this was a great success of this VKS dynamo experiment. However, we have to keep in mind that this dynamo works only with this little trickery by using high magnetic field, which is not what we would like to have from a dynamo, because we don't have ferromagnetism in our Earth core. Anyway, it was a very big thing. Those reversal studies found in the experiment also triggered some new interest in a basic understanding. What is a reversal? What happens during a reversal? So we know it, we have seen it in the Klatzmeier robots, but it's very, very complicated. And people were trying to understand, is there something very, very simple behind? And the very simplest mechanism was given here in a paper in Physical Letters by Petrelis and Fouf. After some algebra, they ended up with a simple equation system. The theta here is just the angle between a dipole and a quadrupole. And you get here an equation with some constant and then sinus 2 theta plus noise. And when you analyze this equation, you find that you get a so-called Zettel node bifurcation. So you have in the space a stable fixed point here, then an unstable fixed point here. If you move here, you might get so-called excursions, which we also know from the geodynamo. But if it is strong enough, you might get a so-called reversal to the other space. So this simple equation is really the absolute most simple that you can imagine to understand the dynamo. Some time before, we were playing with simple alpha squared dynamos, not in the sense of dynamical systems theory, but more in the sense of spectral theory of the non-self-adjoint dynamo operator. And we learned that those non-self-adjoint dynamo operators, they have a very special structure in that they typically exhibit so-called exceptional points where two real branches of the spectrum come together, forming an oscillatory branch. And then we identified the mechanism like so. This dynamo sits here in a stable fixed point. It might undergo oscillations, but sometimes it's going to an unstable fixed point, and then it cannot help but run into the oscillatory branch, make half an oscillation, and come back and settle down again in a stable fixed point. If you look here and here, you see it's only two sides of the same metal. So here we have a dynamical systems picture, and here we have a spectral picture, but it's more or less the same. I come now back to the statistics of the reversals. I said at the beginning that mostly or roughly they are chaotic, but not completely. And this is not known even to a number of geophysicists, that there is some order in the chaos, if you like. And this has been shown in a paper by Consolini de Michelis in Fist of Letters 2003. These two authors were looking for the probability density of reversals over the interreversal time. So I said a typical interreversal time is 300,000 years. And you can take now the probability density. And what they showed is you get peaks. Look only at the red one here. You get peaks, and the peaks are located at n times 95 kiloyears. Do you know what is 95 kiloyears? It's the Milankovitch cycle of the Earth's orbit ellipticity. So for some reason, which we do not know yet, this ellipticity periodicity shows up in the statistics, not as a complete deterministic mechanism, but as some sort of stochastic resonance, perhaps, which triggers with a little bit higher probability a reversal if it's 95 or 190 or 700, n times 95 kiloyears apart. And this is quite interesting. Very interesting here is that this is 95 kiloyears. This is exactly the same 95 kiloyears as we know from the stages of glaciation of the last million years, which is also triggered by the same Milankovitch cycle of Earth's orbit eccentricity. There might be some link, we do not know. What I want to show you only for the moment is the following, that it's only one Milankovitch cycle. We have, of course, precession, 26 kiloyears. Precession means, so our axis is rotating here slowly. And we have nutation 41 kiloyears between 21 and 25 degree. So we have three types of Milankovitch cycle, a little bit simplified, but these other ones are also visible in the statistics of the geomagnetic field, but not so much in the statistics of the reversals. So precession, nutation, eccentricity. Precession is also interesting for the ancient lunar dynamo, which might be explainable in terms of precession or impacts, and also for the dynamo in the asteroid Vesta. So all these mechanical forcings might have an influence on the magnetic field of planetary, of cosmic bodies. And here, this is maybe the most remarkable that we see it also, we see it in the statistics of the reversals. Now I make a little break. I go for 5 minutes from the Earth to the Sun. The solar dynamo is a little bit different from the Earth dynamo. The Earth dynamo is assumed to be a sort of alpha squared dynamos. So the alpha mechanism twice. And I show you here a picture of Eugene Parker, who died in March, and who developed the concept of alpha in this paper here, 55. So the solar dynamo is thought to be a so-called alpha omega dynamo. So we need a so-called omega effect. The solar dynamo is rotating faster than the solar equator is rotating faster than the poles. So we get a winding up of the toroidal magnetic field, but then you still need a mechanism alpha to reproduce the poloidal field. So you need both alpha and omega. Many people are working on the solar dynamo, making very funny, very nice simulations, just as for the Earth. And you can, if you fit the parameters, you can get your 22 years Hale cycle, 11 years Schwabe cycle. Everything seems to be fine. But there is a nagging feeling that there might be something missing in the concept of the solar dynamo. This has to do with an effect which I would like to show you here. If you look, you have a Schwabe cycle, 11 years, which is in principle a Hale cycle, 22 years. If you look into the statistics of this Schwabe or Hale cycle, it looks a little bit as if it were clocked by an internal or external clock. And if you look a little bit more carefully, it looks at the period as 11.07 years. And now we know 1107 appears again in our planetary system. This is a sort of spring-tide periodicity of the alignments of the tidally dominant planets, which are Venus, Earth, Jupiter. So in the four permutations of them, you have a periodicity of 11.07 years. So here you have the sunspots, since 17 sunspots. Here you have the degree of alignment of those three planets, and it's more or less the same. And this is not our idea. It has been found by many people. Here is a good paper by Wilson in 2013. But one might ask, is it pure coincidence or is there some physics? We all know planetary forces are weak. Tidal forces are very weak. And could there be any mechanism which could synchronize the solar dynamo by some weak forcing? And in the last 5-6 years, we have spent some time to understand this. I cannot go very deeply into this one. Our main idea is the following: the tidal forces, which are m=2, making such a motion, so to say, they might synchronize the helicity or the alpha effect of some underlying instability, maybe on the tachocline level of the sun. It might be a Rossby wave, it might be a Taylor instability. We have done a lot of numerics, also experiments now. And it seems that with a little energetic effort, you can indeed synchronize the helicity of this effect. We put it into a simple ODE model, and we found indeed, if we have such a forcing here, we can get the alpha effect synchronized. And by this alpha effect, alpha omega dynamo, we can indeed, by some parametric resonance, synchronize the solar dynamo. We still need a lot of puzzle parts here, but it looks quite good. And here I would like to come back to work that has been done here. Shabatova did very nice work. So let's assume that the tidal forcing might synchronize the 22.14 Hale cycle. What else? We know in addition that our sun undergoes such a very nice rosette-like wobbling around the barycenter of the solar system. So it goes like this. This is governed by Saturn and Jupiter. Essentially, with some wiggles, 19.86 years. So this wobbling has a dominant periodicity of 19.86 years. If you take now the beat period between 22.14 and 19.86, you get 193. And 193 looks very much like the famous Suisse de Vries cycle, approximately 200 years of solar activity. And yeah, this is another paper by Sharp. You see it here again, this rosette-like motion. And now the picture that we have developed in the last year is the following. Let's assume we have our sun is more or less a normal star with the alpha omega dynamo, making whatever period of, let's say, 25 years. And now we have, in addition to this, we have a little bit synchronization of the alpha effect on the tachocline level. We get parametric resonance and we force it, we enslave it onto the 22.14. This is from here to here. Then we add, and this is not understood yet, some spin orbit coupling from the wobbling with a certain 19.86 modulation. And we get here another peak at 193, Suisse de Vries. If we make it stronger, we get other things. We might get even chaotic transitions to so-called bond events, grand minima, so to say. I don't want to speak about Eddie Hallstatt. I don't believe that these are cycles. I think they are chaotic processes, but we can discuss it perhaps later. So we have a certain self-consistent picture now. Many puzzle pieces are still missing, but at least it looks very promising. And what you have done, what you guys have done here in Prague was one of the most important starting points here with charlatans. Okay, so this is summary conventional alpha omega dynamo, first synchronization by tidal forces, then spin orbit coupling, giving Suisse de Vries. We can get also some Gleisberg cycles with 196 years, and we can get grand minima modulation. I would like to skip it here. We do also a little bit climate, which has been done by Václav Bucha. Great work, and you, Pavel, on the interaction of solar magnetic fields and North Atlantic oscillation or whatever. I would like to skip it here and go over to our experiment. So I wanted to show you that we have two motivations. We have geomagnetic field where we see some influence of this orbital forcings on the geodynamo, which is not understood yet. We see that there seems to be some influence of planetary forcings, tidal and wobbling on the solar dynamo. All those things are not understood yet, and we would like to go with our experiments a little bit in the direction to understand something more here. And the first thing which comes to mind is to do at least, not ellipticity or nutation, to do at least precession. So we built a precession-driven dynamo where a body of liquid sodium is forced by precessional motion in a quite complex motion, and we hope to get it done. And I will show you now a lot of color pictures here. So we have built in the last 10 years our Dresden sodium facility for dynamo and thermohydraulic studies. We have 12 tons of sodium. It's a large area here, and we have a big experimental hall. And here is this red one behind. This is our containment where the dynamo is supposed to work. The dynamo is a big machine. I call it now a hell machine because it's really extremely challenging from a mechanical point of view. Essentially, it's a cylindrical volume, 2 × 2 meters, which is supposed to rotate with 10 hertz and precess with 1 hertz. So slower precession. We will need some sort of megawatt for driving the fast rotation. This is not so critical. What is critical is a huge gyroscopic torque that you get from this double rotation, which amounts to 8 million Newton meters. This is here 400 tons here, pulling up, pushing down, and rotating. This is a lot of load onto the basement. And because of this, here it should rotate now. Because of this, we needed a very, very strong basement, which is sitting on some pillars going down into the granite. You see it here, the building of the ferroconcrete basement. Here is the next step was the underframe. It was done in 2018. Here you see is a large ball bearing for the precessional motion. Then you see here on this ball bearing, these pylons are situated where this traverse is inserted in such a way. So we made first a test assembly of all of this, what we call tilting machine. We can change the nutation angle between 45 and 90 degrees. Then all this was transferred into the containment. We need, in the center, we need a big slip ring bringing 1 megawatt of power into the processing frame and bringing also the oil, lubricating oil, into the processing frame, which is highly non-trivial. So here's a motor for rotation, approximately 1 megawatt. It's quite complicated slip rings for signals and argon and so on. And here's the central part, the rotational vessel. This is what is the interesting part, a homogeneous fluid filled with 6 tons of liquid sodium. Okay, this is the vessel. It has to be tested. This was done. And then in 2020, the vessel arrived here in Rossendorf. It's a huge machine. We had problems with these conical end pieces. So the welding was extremely complicated, but finally it was done. It's now here. The bearings are shrinked since 2 weeks. And here's a picture from yesterday, indeed yesterday, where the parts with the conical end pieces together with the bearings are brought to the container. Now we are really on the last 100 meters, so to say, of our marathon to build this machine. Presently, we have we get this installation of the sensors and heating foils. Yeah, it is here, and we plan first experiment on this water for October 22. Yeah, it's moving, if slowly. This is the tilting machine which is moving, and we hope to bring everything together. Andre Giesecke and Federico, who are here, they have done a lot of work concerning preparation of the experiment with a small 1-to-6 experiment to learn about the flow structure, to do numerics for the dynamo. We are very optimistic that we get dynamo action at a magnetic Reynolds number of 430. Technically available is 700. So we have some 1.5 factor available. And here's a nice paper by Federico, Andre, and Jan. It was a nice collaboration on the effect, or what are the effects of the angles here. So it might be that 90 degrees is not the optimum, maybe 80 degrees. So we have to study this. Okay. I'm now, do I still have 5 minutes, or Jan, or? Okay. I come now to the shorter part of my talk concerning the effects that magnetic fields have on velocities, the magnetorotational instability, Taylor instability. But before I come to this one, I would like to show you one of the most essential effects magnetic fields might have on a conducting fluids. And this is Alvin waves. You might have heard this. Hannes Alfvén developed Alvin waves, the concept of Alvin waves in this paper. This is not even half a page in Nature in 42. And he wrote down then this equation here. And the solution is Alvin waves, so to say. He got the Nobel Prize for this half page in Nature in 1970. So he developed Alvin waves concept. What is Alvin waves? Imagine you have a conducting liquid and you have magnetic fields going like this. And if they are strong enough, they act like rubber bands or springs. And then, or the guitar string. And if you make boom like this, then it starts to oscillate. There's a restoring force coming from the Lorentz force, and then you get really like a guitar string. You can really imagine it like this, nice wave. Since that time, there have been a couple of experiments in liquid metals and plasmas. Those, the early ones were liquid metals and a lot of plasma experiments. And one might have thought there is nothing to be done with Alvin waves. Everything has been done. But there was one magic point where no experiments had been done before. And this is the point where Alvin waves are equal to the sound wave. We have heard a lot about the sound waves today. And this is the point which is extremely important for this heating of the solar corona. We get magnetic fields out of the sun. They are crossing the chromosphere, going into the corona. We need energy transfer. And there is a point where you need some transition from sound waves to Alvin waves. And this is exactly here. I show it here. This is the so-called plasma beta 1, as a plasma physicist called it. And we have done an experiment also with liquid metal, but in this case, even with liquid rubidium, which is much more dangerous than sodium. We did an experiment in such a little box here, in such a little container, and we launched Alvin waves by G cross B forcing. And indeed, we have found in our lab in Rossendorf, which can produce now 100 Tesla, which is a lot of magnetic field, at this magic point of 54 Tesla, where sound is equal Alfvén speed, we observed something new. Here are some details from this experiment. And at this magic point, here is a magnetic field going up. We observed, if you apply 8 kilohertz, it's quite boring until this point. And at this point, you get a period doubling. You get a parametric resonance. You get a new signal with 4 kilohertz, which happens only at this point. This is period doubling exactly at this, as it was proposed by Saakashvili a couple of years ago. I skipped all of this. Coming now to the other effects, MRI, I will be very short in 2 minutes. I showed you already this idea, accretion disk, black hole is hungry, would like to eat matter, but it's quite stable. We need magnetic field to destabilize it. I showed it all. And we have done in our PROMISE experiment 2 types of this MRI, 2 very special types, so-called helical MRI with a helical magnetic field applied, and azimudal MRI with the azimudal MRI field applied. We have also done an experiment on the kink type Taylor instability. So there was a lot of activity in our lab in the last 15 years on this. And with DRESDYN, we also would like to continue this type of work by building a huge machine, the same size as a Riga dynamo, where we can do different forms of the MRI of Taylor instability. But this is, some parts are ready, but we have also some delay here. And with this, I would like to stop. Thank you very much. Maybe it was a little bit too long. I would like to stop you, and I'm looking forward to answer your questions.
Thank you very much, Frank, for your talk. And now is time for some questions.
Maybe it's a stupid question, but in the Reynolds equation unit that you've shown, there is a conductivity, and as far as I know from geophysics, conductivity is measured in logarithmic scale, 1, 10, 100, 1,000.
Yeah.
And if you just simply multiply the conductivity with the length, for example, it mostly controls the power of the conductivity, and the other parameters would be not important in this. It's maybe it's.
Yeah, I didn't get the point exactly. So of course we have liquid metals have typical conductivities of 10 up to 6 Siemens per meter. So if you have a salt, some. What you are using, sorry, ammonium, I would guess you get some 10 Siemens per meter. I do not know, but it's indeed, there's a big gap between water with salt and liquid metals. So in principle, but concerning the Earth's core, it's liquid iron. So the conductivity, I don't, Andre, do you know, it's 10 up to 6 or a little bit lower, right? The temperature is high, but it's still a liquid metal. It's a good liquid metal.
It's for liquid metal. So
yes, and so sodium has a 10 times higher conductivity, but it's not that far away.
More or less homogeneous.
Yes, right. There's one problem in the sun. We have, of course, a plasma. And in the plasma, we have huge Reynolds numbers, magnetic Reynolds number. And then I spoke about alpha effect. There's also a little brother of the alpha is a beta effect, that if it's very, very turbulent, your effective conductivity gets down by orders of magnitude. So this means in the convection zone of the sun, with a lot of turbulence, the effective conductivity is much lower than in the radiation zone or in the tachocline, which, by the way, might help in this synchronization mechanism, because this is acting, you need not very much, maybe a ½ meter per second of velocity, because the conductivity is still high, while it is low in the convection zone. But this is more or less typical for plasmas. In the Earth's core, beta effect might also be there, but it's maybe in the range of 50% or 100. It's not very large. It's not very large. Plasmas are a little bit different.
Regarding MRI.
Oh, sorry, I can.
Regarding MRI.
Yeah.
So when you saw the picture, so the outer particle also goes out and the inner particle goes in.
Yes.
So the accretion, it means that also it will also create some outer flow of the matter.
In principle, so if you look in our planetary system, I forgot a little bit the numbers. Maybe 97% of the mass is in the sun, and 90-something% of the angular momentum is in Jupiter and Saturn. So you have a differentiation. So the mass is going in the middle, and the angular momentum is going outwards. This is exactly what happens here. I should look into the numbers, but approximately something like this. It's at a very early stage of the planetary system forming, very early. Then you get all these grains and boulders. It's complicated. I know this, but at the very beginning, you need the MRI to start it. At least this is what most people believe.
Another question is that in the geodynamics, the periods of long non-changed polarity are usually, there is some correlation with plume dynamics and this changes of polarity. Is there any effect of the plume, of the super plumes to these processes?
This is a wonderful question. There's a fantastic book by Coriolis about the connection between supercrones and superplumes. The idea is the following. The geodynamo is, of course, influenced by the thermal boundary conditions. If you get a superplume, you know better than me what it is, and you get a lot of heat away from the core mantle boundary. And approximately, how was it? I think 10 million years later, you get a supercrone, right? Is it like this approximately? Yeah. And of course, 10 million years is a typical time for the superplume to rise up. And there might be a connection. The point is only the statistics is quite poor. We have only we have 2 or 3 supercrones in the geomagnetic reversal sequence. A similar number for superplumes. Yeah, it's hard to make a good statistic from this, but the idea is exactly what you are saying. You are changing the thermal boundary conditions at the core mantle boundary, and by this you change somehow the dynamo and its reversal statistics. But here's the expert. Here's the expert.
We still open question. Some is mechanism of reversals. Why we have magnetic field reversals, but more important is we have, for example, our sun. Our sun is more complicated system, and the magnetic field reversals are almost regular. This solar cycle. Our Earth and Earth's core. It's from this point of view a little easier system, but magnetic field reversals of geomagnetic field reversals of the Earth, it's stochastic. It's so unregular, and we still study how so stochastic are. Probably some explanation is different electrical conductivity of inner outer core, and there are some nonlinear effects. So this correlation between supercrones, superplumes, there are some evidence that it could be coupled, but what's the mechanism? It's just some correlation, but is there physics behind this, or is just correlation, some statistics? That is also important, that there is some physical mechanism of these effects. And of course, geodynamo and generational magnetic field, is influenced by the heat which comes from the core to the mantle. So this thermal boundaries condition and this regulation plays also roles in the frequency of reversals. So it's not so easy to answer, but we have many correlations, but what's behind this correlation? It's some physics or it's just some statistics?
Maybe I can add maybe one thing. So typically alpha squared dynamos are in most cases more or less stable, but you might get sudden reversals. Alpha omega, like the sun, or Riga is also a sort of alpha, they are oscillatory. And now what we noticed in our very simple dynamo studies is that there might be, if you take an alpha squared dynamo, it was an observation by Axel Brandenburg, and we did it also. If you take an alpha squared dynamo to make it very strong, so it is, at the beginning, it's very stable, but the stronger you make it, the more you drive it into a state where it becomes sort of prone to reversals. It looks a little bit like Sandpile or self-organized criticality. So you make it very strong, and then it's always at the edge of chaos. Due to the saturation, so to say. It's quite funny. We have a couple of papers here. I'm not quite sure, but it might explain that such a reversal is not something very special. It might be if you have a strong dynamo, such as the Earth, it's very natural that it goes into a state where it's close to chaos and close to reversals. But I think nobody has taken up this idea. Maybe, Jan, you should. Maybe.
I asked this question to Paul Roberts, and he answered me that, similar as you said now, that probably these geomagnetic reversals are natural character of this nonlinear system which is inside the Earth's core. So geodynamo is a nonlinear system, and it's typical for this system that produce magnetic field reversals. So this polarity is probably some result of these nonlinear processes, and it's a character. So it's one idea is that there is no special mechanism. It's just characteristic of this system, and times to time some polarity changes can occur. We will see in the future. So, some other question, or then we can finish. And Frank, thank you very much. And as